Is that true? Does anyone have any technical questions, content questions? No. All right. So this first chapter we're doing, chapter 2, it's going to start at a very basic level. We're going to eventually talk about the different types of numbers. We are, in this chapter, going to talk about, I think this came up last time, Roman numerals and Egyptian numerals. Did this come up last time? I can't remember. Egyptian hieroglyphic numerals. Does that sound interesting at all? Like the way that the Egyptians would have represented, this is like ancient Egyptians, would have represented the number 7 or something. Yes? Okay. Does anyone know the name of our numeration system, the name of our numbers that we use? We have an actual, it isn't ours. I mean, we borrowed it from another civilization. Anybody know? So the numbers that we use.
Arabic?
Yes.
Hindu-Arabic.
Hindu-Arabic. So we use the Hindu-Arabic numeration system. And there's a lot of cool stuff. I'm probably going to bring some stuff to show you the evolution of the shapes of what we consider to be the numbers, right? And by the way, okay, so we have a lot of levels to numbers, right? So we have numerals and we have numbers. Right? So the numeral is the symbol we use, and the number is the idea of counting. So I don't care what language or whatever, if I have 2 rocks in my hand, I know the idea of 2. We call it 2. That's the word we use. Yes? If you have Spanish, you call it dos. If you have French, un, deux, trois, you call it deux, right? And so forth. And you guys probably, maybe some other people know some other languages. But also throughout history, there have been a lot of ways to represent that with a symbol. We use the symbol 2, and of course that's backwards, but all right. The Mayans, I love the Mayan numeration system. Just go with me for a second. In the Mayan numeration system, a line is 5 and a dot is 1. So to write the number 7, it would be a line with 2 dots on top. So I like to call it pancakes and blueberries, right? So like 2 lines and 3 dots would be 13. 5, 5, 1, 2, 3, 13. Does that make sense? Okay, I like it. And that's one of the coolest things. You guys might not have the most opportunity to get into this. But when I teach math class, I do every now and again like to say, why does the square root symbol look the way it does? Did it have to look that way? Why do we put exponents where we do? Did we have to do that, right? Just to kind of make people realize aliens didn't come down and say, use this symbol for square root or we will come back and destroy you. We're like, oh shit, no. We created the damn symbols, right? They could have been any number of things. Are you guys semi with me? Okay. All right. So what we're going to start with is the idea of sets. And does anything come to mind mathematically when I say the word set? I don't know if anybody's ever played the card game set. I can get very frustrated. When I say the word set, does that mean anything mathematically to you? Yes? Oh, okay, so a bunch of numbers, multiple numbers, kind of grouped. I like it. Anybody else? Somebody else had their hand up. Same thing. What about set notation? Right, so a set could be 1, 3, 9. There's a set of numbers. But we normally kind of like make sure they're grouped by putting those little squiggly lines, right? Now they officially should look like that. But when I draw them, I often don't pay enough attention. So they end up looking like a real squiggle. Okay. You guys have seen those before. Is this true? Yes. Okay. So that's your basic set notation. And we normally denote sets with capital letters. Like we can call that set capital A. So let's say set B, let's say that set B is 4, 7, 9, 11. Okay. Very exciting. Okay. let me ask you this. Is 3 an element of A? Yes, so an element of just means a member of. The symbol for element of, so I'd say yes, 3 is an element of A. It's a little E. I don't know if anybody's ever seen that notation before. Kind of makes sense, a little E for the word element. It's nice. Okay, how about is 3 an element of B? Nope. So what do you think? Hazard a guess. If I am not allowed to skateboard, I'm going to see a picture of a skateboard with what? Line through it, yes? So how do you think I say 3 is not an element of B?
Element description.
Yeah, element symbol with a line through it, yeah. So the way to read this is 3 is not an element of B. Kick ass. All right, I like it. Let's see, I got some notes to keep myself straight here. Otherwise, I'm going to go off on tangents. Blah, 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 blah. Oh, so we could describe sets verbally. So I could say the set of all students who have brown hair in this class, right? So then I'd have like squiggly line. So I could just say it verbally, the set of all students who have brown hair. Or I could do it, so set of students with brown hair. Or I could do it set notation, which would be, I would just start listing names of students, yes? Or I could do something called set builder. Which would be this. X such that X is a student with brown hair. That last one seems kind of dumb because it's basically the verbal with some set stuff thrown around it. I've never liked the idea of set builder, but oh well, that is a valid, it's time. That is a valid way to do it. I like it. Has anybody ever seen that set builder notation before? Does that look familiar at all? No? Okay. So if I ask you to list, can you list all the numbers that start with the letter T? Do you want to list all the numbers that start with the letter T? I'd much rather write X. So the way you read this is X such that description, right? So you could say X such that X is a number that starts with T. That's set builder. Which is basically the same thing as verbal. Okay. Stop for a second. So let's get into a little more interesting stuff here. Let's get into some more mathematical applications with these sets. Let me create some more sets up here. Let's see. Let's say set C is, here I had a specific, yeah, sure, let's do some letters. Set D is, let's do, sure. Set E is, yep. And set F is, yeah. All right. By the way, I am going to lecture for a little while. I have a little handout for you guys to work on together. So I like to not talk the entire time, because otherwise we're going to go crazy, me included. So let me see, let me ask you this question. Is this true or false?
True, right? That just says A is in C. Yes, A is part of C. I love it.
True. Okay. What about this statement? You could do it, Jeff.
True, right? Is G an element of F? No, G is not an element in F. That's what that says. That's true. I love it. Kick ass.
By the way, I don't do true false too often, but my most favorite thing I've ever seen students do is that.
I love that. Do you guys see what I'm saying? And then I say, is that a T or an F? And they say, this has actually happened. What was the right answer? I'm like, really? What opinion do you have of my intelligence? What are you talking about? Right? So all right.
So I normally ask people to spell out the word, so I don't get that business.
Okay. Let me see what you guys know about some symbols with this stuff. Well, yeah, we're going to do that in a minute. Yeah. Let's do this first. Does anyone see any of the sets that are contained in another set? Is there a set that is contained in the other one? Which one is contained in which one? E is contained in C and E is contained in F, correct? Now, real quick, what's true about C and F? They're equal to each other, so we would say C equals F. Okay. I'm going to come back to this in a minute. We could also say that E, so here's kind of new notation, but it feels a lot like inequality symbols. E is a subset of F. That symbol there means subset. Gather. Okay, so sort of like the less than symbol, but it's a little more descriptive than less than. Like 6 is less than 7 all day long. Does this have less elements than this? Yes, but is E a subset of D? No. Subset means it's contained within. I love it. So 6 is definitely less than 7. Yay. Is 7 less than or equal to 7? Totally, because I just added the equal sign, right? So watch this. We said C equals F, but is this also true? What do you guys think of this symbol here means? Yes.
Like greater or less than or equal.
Sort of. Is a subset or equal to. Is that cool? So C is definitely a subset or is equal to because it's equal to. Just has to do one of the two things. I like it. Okay, I like it. So this is nothing too crazy yet. In fact, some of this stuff you probably have seen before. Even if you haven't, it's nothing too insane. What about... I keep wanting to do this, but I'm not ready to do it. Good. Oh, okay. Are any of these completely not related to each other? Do you guys see what I mean? Which two would you say are completely not, or which ones? Which one especially? Which ones? D and E are totally not related to each other. What about C and D? Don't they have a little bit of overlap? Okay, so D and E are called disjoint because they have nowhere where they join. That kind of makes sense. It's not disjoint and dat joint. It's just they mean they don't join together. They have no, I'm going to say this word, intersection. I like it. So we all know the word intersection from everyday life, right? You can imagine that. But does anyone know what it means in mathematics? Like, can somebody try to think about what the intersection of C and D, what would that be? Yeah, these two intersect at F. So intersection really just means what do they have in common? So the symbol we use for that, is that the two I said? Yes. Is that symbol. Got it. Let me stop for a minute. Has anybody ever seen that symbol before? No? No? Okay. The way I remember it is sort of like intersection is sort of related to the word and. If I said what's in C and in D? F, correct? So intersection is like and. So the letter A, if you erase the middle bar, it looks like that symbol. I don't know if that helps at all. You with me a little bit? Okay. What if I say, what is in, sure, E or D? I want everything that's in E or D. So I love that symbol, by the way, because I imagine like a parent and they have kids and it's like, good Lord, you or you, somebody cleaned the room. Yeah, there's a symbol, okay, or, right? Or is this good way, and the other one is like an A that lost its middle bar. You with me? What is in E or D? Yes. Yes. A, B, C, D, F, G, X, right? So this is basically the idea of and. It's also intersection. This one is or, and here's another reason why this symbol makes sense. The word that it goes with is union. If you create a union, don't you put several things together? So that's why that kind of makes sense. I like it. Quick word about and or. Whenever I teach probability especially, so you have these words in probability, I like to think about the and the or as bouncers at a club. So if I go up to a club and it's the and bouncer, he says, all right, to get in the club, you got to know Joe the bartender. I know Joe the bartender. And you got to dress nice. And you got to have a lot of money. Dude, I'm out. I can't go in. So and will always make the answer smaller because things that get in have to meet all the requirements, correct? So like back in the day, nowadays you guys don't have this because you got the internet and all that stuff. But when I was in college, you would go to the financial aid office and there was a book like this big that was scholarships. So you'd sit down with this book and then you would, okay, must be a math major. You know, you could get $10,000 scholarship if you're a math major. Check. You have a GPA greater than this. Barely. You took this class. Yes. And then at the very bottom it says something like you are over 50% American Indian. Shit. Turn the page. So those are all ands. Yes? Every time I read a new one, the pool of people that could qualify gets smaller. If I go to the bar and the or bouncer is there, and I come up and I'm like, hey, can I get in? He says, all right, you gotta be rich. Shit. Or, you gotta dress nice. Shit. Or, you gotta know Joe. I know Joe, and then I get in. So there's more people in the bar. Okay. Or more. It's crazy. Yes. So see here, the or answer was big, and the and answer was small. So and will make things generally smaller, or will include more people, so it makes the answer bigger. All right, let me stop for a minute, because, okay. All right. So I don't know if any of this sounds familiar, if you've done any of this before. Oh yeah, that's silly. If I put, just to make sure everybody's with me, if I put set G was BA, how do these relate? These two? They're the same. I love it, right? Just put that one out of alphabetical order, just be different, right? Blah, blah, blah. Also, if I said, what's a good example of this? If I said, okay, you got a bunch of M&Ms, I'm like, what colors did you get? And you said, well, I got blue, and blue, and blue, and green, and blue. I'm like, good Lord, you already said blue, right? So if there's repeats, you don't put them twice. So like if I did, let's do this. If I do C or E, C or E, what would the answer be? ABF. Right? You don't put ABF, AB. You don't repeat things that are already there. Very basic things, but just to throw that out there. Okay. Any questions about all this stuff? So the important things for you are the symbols that you might not be the most familiar with and what they mean, right? A really nifty thing to tell students about symbols as they learn them is, for example, if I ask you guys, what's the square root of 16? You guys feel pretty confident it's 4, right? Why is it 4?
Because 4 times 4 is 16.
Kick ass. So you have internalized the question that symbol represents. So most of mathematics is just people like me who either can't write well or don't like to write a lot. And we're like, let's just make whole sentences and paragraphs, let's just make them into symbols. And then every student who comes along is like, you guys have to catch up with this now, right? That's basically what that's math in a nutshell right there, right? So one nice thing when you're teaching a student a new idea, you refer to old ideas and you say, remember when you first learned that? You didn't have it internalized yet. That's where you are with this new idea. I do exactly that with some of my, like with my pre-calc and my calculus class, because they learn all these funky new symbols, and I'm like, well, you were at the same place with that a while back. Now you're there again with this symbol. Okay. Blah, 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 blah. Yeah. Can I make, let's see. I need to make one more. Let me make some new ones. Yeah, I'll make some new sets. Are these sets equal to each other? No. But what is the same? The size of them, right? The number of things in them. So we can't say that A equals B, but we can say there exists a one-to-one correspondence. Oh, shit. Between A and B. You guys kind of with me? Do you remember in algebra making XY tables? You were creating a correspondence. It wasn't always one-to-one. One-to-one means, for example, the simplest kind of algebraic correspondence I can make. How do these numbers relate to each other?
The top ones are squares.
Yeah. So I would say these are the squares of these. So 1 corresponds to 1 squared, 2 corresponds to 2 squared, 3 corresponds to 3 squared, right? So the algebraic correspondence would be y equals x squared, that kind of thing. Are you guys with me? And then one set would be the inputs, the x's, and the other set would be the output, the y's. Do you see how this idea of set shows up in almost every math class? Right? You talk about domain and range, those are sets. Yeah.
I'm so sorry, you changed letters. You said in relation to this, which one would be y?
Oh, I'm sorry, yeah. The input would be the b's, and the
Okay.
output would be these.
Got it,
right?
okay.
Now, if I made my algebraic correspondence the square root of,
Mm-hmm.
this would be the inputs, this would be the outputs. Is that
Okay.
cool? Right.
Got it.
Okay. For us right now, it doesn't matter, they're just two sets. There is a one-to-one correspondence. Okay, I like it. So as long as the sets are the same size, we can have a one-to-one correspondence. Does that make sense? It doesn't have to be the way I said. I could just say 1 goes to 9, 2 goes to 1, and 3 goes to 4. I don't need to have an algebraic. It's just one way I could have a connection. Let me stop for a minute. Okay. Does a set have to be finite? Every set I've put up here so far have been finite. How would I represent an infinite set? Like, who knows what the whole numbers are? Hote? Whole numbers. Does anyone know what the whole numbers are? Good. The way to remember whole numbers, it's the natural numbers, the thing that came naturally to us, 1, 2, 3, and we add the number that looks like a whole. So we call it the whole numbers. It's crazy. It's not y, but it's just neat to realize that's a way to remember. How would you want to list all of them? So how do we represent? Keep going. dot, dot, dot. So whenever I see that, I've set up a pattern, and it just continues forever, right? So how large is that set? Infinite. There's an infinite number of things. How would you represent the set of even numbers? Or let me say, screw it. I should have done natural numbers. That's all right, I'll be fine. How do I represent the set of, damn it. Can we change this? Change this to start at 1. Of course we can, Jeff. Okay, so we'll make it natural numbers. Try to make a specific point. So natural numbers are 1, 2, 3. Whole numbers are if I add 0. And the neat thing about the idea of 0, do you guys understand that 0 had to be invented? The Babylonians, for a large part of their existence, they didn't have a symbol for 0. They did eventually make a symbol for 0, and then not too long after that, their civilization collapsed. Right? They were like, oh shit, we're done. Okay. So it's kind of neat to realize that, the reason we call this the natural numbers is what came naturally to us. 1, 2, 3. How do you describe the even numbers, the set of all even numbers? 2, 4, 6, and then dot, dot, dot. Anybody have an idea? Are either one of those sets bigger than the other one? Do you see why somebody might think so? If all of you think they're equal in size, why would somebody think one is bigger, and which one would they think is bigger?
2, 4, 6.
No. Aren't these numbers in here? Doesn't this one then sort of have more numbers? Does this one have the number 1? Does it have 3? Does it have 5? Does it have 7? So now let me ask you to rethink. Do you guys still think that they're the same size? They are the same size. Damn you, Jeff. They are the same size. Can I do something to these to make them become these? What would I do to these? Just double them, right? Double 1 is 2. Double 2 is 4. Double 3 is 6. Doesn't every single one of these go directly to one in there? Aren't they the same size? Okay. That's just, man, Jeff, you went there today. That's just one of the weird things about infinity. Infinity is weird. Yes? What do you guys think about infinity? When I say infinity, what comes to mind? Never ending. The symbol, I love it, the symbol. I like the symbol because it's sort of like the word banana. It's like, where do I stop? Right? I was just wondering, what is that? Anybody else, a different thing come to mind about infinity? Space, I love it. Because we're not even sure. We have a pretty good idea there's probably an end to the universe we're in, but we don't know. Maybe it goes forever. Okay. These are both what's called countably infinite. Let me go a little further just because I want to. These are both countably infinite. In fact, do you see how this is almost by definition countably infinite? 1, 2, 3. If you wanted to, you could do that for as long as you live, correct? So you could just keep going. It's countably infinite. How many numbers are between the number 0 and 1? How many numbers are between 0 and 1? No, numbers, just numbers. How many numbers are between 0 and 1? Is the square root of 2, is the square root of 0.9, or 0.9, is 0.9 between 0 and 1?
Yeah.
Is the square root of 0.9 between 0 and 1? Yes. Is 5 divided by 8 in between 0 and 1? Yes. So how many numbers are between 0 and 1? Infinite. You with me? Okay. Now to really trip you up, how many numbers are between 0 and 0.1? Infinite. How many numbers are between 0 and 0.01? Infinite. Right? So that's what we would call an uncountable infinity. Because I don't care how much I cut it up, it's still another infinity. It's like, holy shit. Okay. I went a little further than I had to, but that's going to happen. Because I kind of like math. I'm sorry. I'll stop. Okay. So this is what you call countably infinite. They're both infinite sets, but they're actually equivalent to each other, because you can build a correspondence, right? Okay, maybe. Okay. Blah, blah, blah. Blah, 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 blah. Okay. Let me put a picture up here and see what you guys think about it. Let's do sure. Republicans, bowlers. Why not? Just happened to come to mind. Does anyone know what that's called, that diagram? Venn diagram. Kick ass. Why does it make sense that those two circles are connected? What does that connection represent? Who is this person right there? It's a Republican bowler, right? Somebody who bowls who is also a Republican, right? And it makes sense that there's probably some Republican bowlers. Okay, I like it. Who is this person right there? Yeah, that person is not Republican, doesn't bowl, right? Let me ask you real quick. If they're not Republican, are they Democrat? Why not? Do you know how many political parties there are? A lot is the right answer. Some people might say 2, some people might say 3. Do you know how many candidates for president there were? At least in the 2016. I'm not sure about the last one. Most people only know 2. But if I remember correctly, there was 1,024. If I remember correctly. There's at least 53 political parties. And there's many people who just sort of run not affiliated. So each party had at least one candidate. And then there's people who just ran. And we don't know about them because they didn't gather enough signatures or whatever to get on ballots, but they were there. Sorry. Don't know why I went that way. Okay. So Venn diagrams, at some point you guys have all worked with these. So let me make one with some numbers. Let's do this. This is let's make this apples and bananas, just to make it a little less boring than A and B. So I ask somebody, what's your favorite fruit, and this is what they tell me. Or what fruit did you last eat? I don't know. Somebody. Who are these 11 people in the middle? They like apples and bananas, or they ate apples and bananas, whatever, right? They did both. So does anybody know the symbol I can use between apples, bananas to represent that middle part? The symbol we saw earlier? Yeah, intersection. So you see, doesn't it make sense that's the intersection of the two circles? That just makes physical sense. So thank God that's what we call it. It's the intersection of those two circles. How many total people answered apples? Nope. 15. How many people answered both apples, bananas? 11. How many total people said apples? 15. You guys with me? Because you're going to have to create a Venn diagram backwards. I'm going to tell you 15 people liked apples, 11 like apples and bananas, and you're not going to see the number 15 anywhere. Because together they make 15. Are you with me? Okay. How many people said bananas? How many total people did I talk to? 27, 11. You guys see that? Okay. Kick ass. Last little thing here, and then I'll let you guys try out this worksheet. Let's see. So on this Venn diagram, how would I represent? If I wanted to shade this in, this should be easy based on what we just did. Where would that get shaded in? In the middle. I love it. That's A intersect B. What about A union B? Just the whole thing, right? Bam, 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 the whole thing, bam, 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 right? What about well, make that big, Jeff. What about not A, otherwise known as a complement? So I want to shade in everything that's not A. So I just okay, the box around A, and also the parts of B that aren't in A. I love it. So the only thing not shaded is circle A. Nothing too amazing yet, right? This is pretty, hopefully straightforward. What about this? Let me just put this up here and see what you guys think. Become a B. Still looks the same. So I want you to shade in what that refers to. What do you think? Yes?
When you shade both circles and then like essentially erase the B, like, but then take your eraser and just like, you essentially are
Yes.
just shading the A only, but yeah, like
So shade the A, but leave what blank?
the middle.
The intersection, right? So I want to have all of set A, but take away anything that's also in B. That's basically what that means. So I just shade this in. Just leave that blank. So if I want to do a little less visual of a subtraction problem, of a removal, so like the stuff we had earlier, if A was 1, 5, 8, and B is 8, 9, 11, 13, A minus B is what? 1 and 5, that's it. So it's not like our subtraction because these don't even bother me. I don't care about those. I just want set A, take anything away that's also in set B. So this would just be 1 and 5. Kick ass. Okay, I think we might be ready. Yeah, let me see. Is there one like that? Yes, there is. Let's do that. Okay. All right. Last little idea before I give you this. This is basically the end of section 2.1. There's this interesting idea. Real quick, do you guys know the official name of the XY plane? Anybody know what the technical name is for the XY plane? I say X and I do this all the time. The XY plane. Cartesian coordinates. Anybody else know why it's called? Anybody? You guys have heard Cartesian before? No? Okay. Anyone know why it's called a Cartesian? And you're like, dude, I just found out it's called Cartesian. What do you want? There's this guy named Rene Descartes who. There are several urban legends in mathematics, and you would never make a movie out of them because they're pretty boring, but still. The urban legend about Rene Descartes was he was sick in bed, and he was watching a fly on the ceiling, and he's like, I could describe the position of that fly with how far away it is, so he came up with the XY plane. Who cares if that's true? Who cares? Whatever he did, he made it up. So there is something called, and by the way, how do I identify in a Cartesian plane a location? What does it take to identify a location on an XY plane? How do I identify one location?
How far away it is from X and how far away it is from
And what do we call that?
a point.
A point. So the point's got two parts, right? The X distance and the Y distance, correct? You guys with me? So they look like points. So there's something called the Cartesian, right? So now we're not going to be freaking out about the word Cartesian. It's just the guy Descartes, we gave him props by making this word, right? Cartesian product. That's a little long. Let me make some new ones. So let's say that set W is X, Y, and set let's not make it X. Set M is M, N. Sure. the Cartesian product would just create all the points I could make where one is the first element and the other is the second element. What do I mean by that? I mean, so believe it or not, here's the symbol for the Cartesian product. Thankfully, it's just our old time symbol. This is just going to be a collection of all the points that you can create where one is like the input and the other is like the output. And basically, whatever I list first are the inputs. So for example, one point I could make is xm, correct? Right? What's another point I can make? ym, sure. And xn and y. I love it. That's the Cartesian product. What I should have asked you, and I didn't, is how big the answer was going to be. How many points did we end up with? Why does that make sense? Because there's 2 elements here and 2 elements there. So for every element here, there's 2 that it can go with there. So 2 times 2 is 4. So if this had 3 elements and this had 2 elements, how many points would I end up with? 3 times 2, 6. And you see how that kind of correlates to this? So 2 times 2 is 4, and that kind of relates to the size of the answer. So we sort of borrowed this notation for our multiplication. Let me slow down for a minute. Everybody sort of with me? So the name Cartesian product sounds horrific, but all you're doing is making all the pairs you can. That's all you're doing. If this would have been M cross W, what would the one thing that would be different? Yeah, each one would have just been turned around, right? Okay, I like it. I like it. All right, so let me finally shut the hell up. Bore myself sometimes. I'm going to give you this. I want you guys to like find like 2 other people near you to work with, right? A little review of section 2.1. There's 2 for you guys here. There's 2 for these guys here. There's 1 for her back there. Okay. All right, guys, let's take a look at this stuff here. Oh my God, help us. Okay. So I did kind of spring you on this at the end, and I'm sorry about that. But this just sets up, because otherwise a question like not be would suck a lot, because it would just be every other number. So this is every number that could possibly be in those 2. Intersection's very straightforward. Intersection kicks ass, because it's just what's in common. So what'd you guys get for the intersection of A and B?
7 and 26.
7 and 26. That one's beautiful. That is whatever's in both, kick ass, right? What's not in B? You have to know what the universe is so you know what could have been in B. So you know what ended up not being in B. So what ended up not being in B?
0, 3,
0,
4, and 18.
3, 4, 18. I love it. All right. And then I think what quickly became everybody's favorite problem was number 3. So here's the way to look at this. When you have a union question, you only care about the sets that you're uniting. That's it. Don't look at any other freaking set. I'm uniting A with not B. That's all I care about. So the intersection really clear, just what do you see in both? Union, you want to just make one big group out of both of these guys, right? So if I wanted to combine, oh God, a group of Republicans with a group of bowlers, are there anybody that would be both? Yes, there could be some. But so I wouldn't include them twice somehow. I wouldn't clone them or something, so we want, because I'm not allowed to. That's against the law. But plus I don't know how to. So what I mean is, the answer to a union, you should always be able to find each set in it, because it's got to include at least that much. So it's going to be everything that's in A, so I'm just going to write all this stuff in A. I know that's a part of the answer. Everything in A, or in not B. So what have I not written yet that's still in not B?
0 and 3.
There you go. So can you find all of each set in the answer? There's 0, 3, 4, 18. That's not B, yes? There is 4, 7, 18, 26, which is A. Do you guys see what I'm saying? That's why the answer to union will almost always be bigger than the original sets, because it includes stuff from both sets. Okay, maybe. Intersection, almost always smaller than both. Union, almost always bigger than both. When would that not be true? Well, if both sets were equal, because then the intersection and the union would just be the same thing again. Does that make sense? So if I had, for example, if I had C is 0, 4, and D is 0, 4, what does C intersect D?
0,
0, 4, and what's C union D?
4.
0 freaking 4. Okay, that's the one time it doesn't get smaller and it doesn't get bigger. And this is kind of like not a very interesting example, right? They're just both the same. Okay. But in general, the intersection will always be smaller than either one. The union will always be bigger than either one. This guy is weird because our brain is trained to see the minus sign a certain way, but that's how the minus sign interacts when it's between numbers. This is between sets, so it's not quite the same idea. I think of it as a remove. Take set A, remove everything from it that's also in B. That's what that means. So if you take set A, the great thing is we already know what's in both. So just take set A and remove these. Does that make sense? Take set A, remove anything that's also in B. What would I be left with? 4 and 18. Kick ass. Real life kids. Okay. Now this one, I hope to God nobody tried to write all the answers because they didn't ask for that. Just how many elements would it have? So it'd be a bunch of points, but how many points would you end up with? How many elements in A? 4. How many elements in B? 4. So you'd end up with 16. And yes, one of them would be, for example, 26, 26. Right? You can have a point 26, 26. That's a valid point. So in this case, it doesn't matter if there's a repeat. You still put them together. Okay, maybe. So this is kind of like, this stuff feels a little familiar because it's sort of related to all these other things you guys have done in math. But this is the more fundamental stuff that those are built on. Okay, maybe. Oh yeah. Yeah, so English teachers of the past hated double negatives. This is basically is 4 not an element of not B? So that's an exciting, like, lawyerly thing to do. Not B, does it have 4 in it? Does not B have 4 in it? Yes. So is it right to say 4 is not an element of not B? No, so this is false, no. 4 is in that set. So if you say it isn't, you're wrong. Okay, maybe. Some of you guys look at me like you want to hurt me, I'll be all right. Number 2, how many of you guys tried number 2? Because this, I warned you it was coming, but we haven't done an example. I just wanted to see how you guys would handle this. Who feels like they got the answer right? Look at that, I love this shit. Come on up here and draw it.
All of us?
No, who said they feel like they have the answer right? You want to come up? Okay. a good marker. Sorry, give you a bad marker. All right. Did everybody see that well enough? Is that what you guys, anybody else get that also, or? Let's take a look, let's break it down. So I'm gonna analyze this. And I appreciate the, you coming up. So let me see. You've got, you put 14 there, and then
3, and then 2 in the center, and 17 on the other
3,
side.
2, 17.
Oh, I
And
forgot
each,
to label them, that's my bad.
each circle is what now? Yeah, what's this first circle?
The 3 is the left hand, and then the right is the artistic.
All
and
right,
then
so
the
let's
2
double
is
check
the-
this.
the bow.
The place you always want to start with these kind of problems is the innermost. So 2 are both. Okay, that's good so far, right? This 2 are both. How many total are supposed to be in the left-handed circle? Let me zoom out a little bit. How many total are? Oh crap! All right. How many total are supposed to be left-handed? 5. Is that true?
Yes.
How many total are supposed to be artistic? Is that true? Yes. How many do we have in the circle so far? 22, right? And there's 38, so the one little thing is this, you might have said this, I might have seen it wrong, but what should this be out here? 16.
I just don't know how to count.
I understand. So when you get this kind of problem in the homework and they give you, you're gonna get some that, you'll be excited to hear about this. You're gonna get some that look, well, they look like this problem here. You always start with the amount that match all 3, and then you work out from there, right? Okay. So that's the answer for that one. What about this? Which regions correspond to A intersect B? That one should be nice. 2 and 6. What about which regions correspond to B union C? What are the only regions that don't? 1 and 8. I love it. So that'd be 2, 3, 4, 5, 6, 7. Cool. And then part C, I apologize. I have no idea when I created this. I just was really. How would you denote the region comprised? Okay. 5, 6, 2. What symbols would you use? It's just like these symbols here. Does anyone think they have an answer for that? Yes.
A intersection B, all union with A intersection C.
Ooh, okay, wait. So A intersection B, union with
A intersection C.
Okay. Everybody think about that for a minute. See what you feel about it. Let's see. You guys think that looks like it's right? Yes.
The line above them so that it says everything except A and B.
Oh, is that what you said wrong? No. So where's A intersect B? 2, 6. And then I want to union. What's A intersect C? 5 and 6. So if I union those, don't I get 2, 5, 6? So that'll work. There's another way to do it. So 2, 5, and 6. Well, the other way's about like this. So I want to get these guys here, right? So isn't that like A intersect with B union C? So if I do B union C, that's basically all of B and all of C, correct? And if I intersect that with A, that will be 2, 5, and 6. Now, real quick, that last problem, definitely the freakiest problem on there, right? That's the one I'm just kind of pushing you a little bit to see what you think. Yes?
Why is it a union and not an intersection?
Oh, right here? What was A intersect B again? Which regions?
5 and 6.
Well, that's A intersect C, right? So let's see.
Oh.
A intersect C. Oh, hey, little dude. Oh, you just like it. Oh my gosh. All right, I'll let you. Oh, he's gone. Okay. A intersect B would be 2 and 6, correct? A intersect C would be 5 and 6. So sure enough, if you union those, you get 2, 5, 6. So that I agree with. I want to ask you guys, I don't know if you guys agree with this one. If I do B or C, that's all this, and where does A intersect with that? Right there. So I'm going to go just one step further than we have to. I just want to point this out. If I sort of distribute this, don't I get A intersect B or A intersect C? So we're not going to do that. Don't freak out. There is a whole math to this set notation that you could do where you have, they're more like logic laws. There's stuff called De Morgan's law, so you don't have to worry. But it's kind of neat that it does look sort of like distribution, right? Okay. Okay. So this was just section 2.1 practice. I think I said this earlier, right? I'm trying to get copies of the first couple of homeworks. I'm going to put them up in Canvas the minute that I'm actually able to do that. That doesn't have all the answers included, right? I have no idea why the answers kept showing up. What was the other thing I wanted to do? Yeah, I wanted to look ahead a little bit. Of course, I can't log in there. I do want to do one more thing today, and I think I'm going to let us out here because I am feeling very scatterbrained. I apologize for that. What's coming up pretty soon in this next section? So again, just to remind you guys, our number system is called Hindu Arabic. Look. What base is our number system? Base 10, and the really good theory about why that is because we have 10 fingers, right? So what does it mean for it to be base 10? What the hell does that mean? Well, that means, do we have what's the highest single digit thing we have a symbol for?
9.
Yep, 9, right? We have a base 10 number system. Do we have a single digit way to represent 10? No, it takes 1 0, correct? So the idea is, when does the speedometer roll over is the minute we add 1 to 9. Then I have to have a whole other place. Are you guys with me? We are eventually going to talk about different bases, and I just want to kind of lay the groundwork for this. Some of you guys, if you're lucky, how many of you guys want to teach like 1st, 2nd, 3rd, 4th grade, like up around there? Yes, okay. How many of you want to teach 7th, 8th? Okay, that's normal. Okay. So that explains my 8th grade teacher. But if you are lucky enough to get one of the lower grades, the weirdest thing for you is going to be the fact that those students have never, unless their parents do something with them, which can you always trust that to happen? No. Those students might never have been exposed to the idea of a base 10 number system, because all of us are like, number 11, I know what that is. They're not going to have a freaking clue what 1 1 is. Some of them might say that's 2. And you can see the logic of that, correct? So during this semester, I'm going to be showing you videos of students of various grades working math problems. And then we're going to discuss the mistakes, but what was the logic behind the mistakes? And then what would we do with the student to help them go from what they have now to where they need to be? Does that make sense? So I told you the first day that one of the most important things you guys can do, I don't care how you feel about math, the minute you're an elementary teacher, you better represent math well, because you are laying the groundwork for the future. So some of you guys, if you don't like math, you could trace that back to some of your earliest teachers, where they weren't flexible, they didn't try to meet you where you were logically, they just said, you're doing it wrong, look at the way we did it, right? That turns you off. That's some of you guys. That's some people, definitely. So, dear God, if you hate math, you got to do something about that, because that's going to come through. That's going to translate to them, right? So one reason why I teach you in this class, not just me, but this class, teaches you base 8, base 6, base 16, base whatever, instead of just base 10, is so you can feel the way your students are going to feel. Do you understand? They are going to be learning, and we got some cool ass manipulatives that we're going to take to represent base 10. It's going to be neat. So yeah, every now and again I'm going to bring out a bunch of stuff. I'm going to hand it out to everybody, and you guys are going to play with all these cool little manipulatives. You're going to be basically your students playing with this stuff. So when we do something like base 8, base 10, what's the highest single digit? 9. Base 8, what would the highest single digit be? 7. How would you write the number 8 in base 8? 1, 0. Right? Freaky. Real quick. Where's my, there you are. Winner. That's not going to be good enough, Jeff. Off. There. Okay, just for a moment here. I really want, this is one of the coolest things. There's a class I teach. I used to be able to teach Math 120. I used to teach number systems. So I think I told you this. We're going to learn Roman, Egyptian. I might mention, like, I think Mayans in the book too. But I also taught them Babylonian number system and so forth in this 120 class, right? And then I had them create their own number system. And that was a project they had to do. So I had some really creative stuff. Holy crap. But anyway, base 8. So base 10. Why is it called base 10? Because, let's even go to decimals. Why not? What place is this in? Hundreds, which is 10 squared, correct? This is 10, which is 10 to the first. This is the ones place, which is 10 to the 0, yes? Anything to the 0 power is 1. What place is this? Tenths. See how I keep dividing by 10? Tenths, which is 10 to the negative 1. Let's keep that going, Jeff. And this, of course, would be hundredths. And then it just keeps going forever in both directions. Whoop-de-doo. So, what would base 8 look like? It's the same idea. Right? So let's start here. This would be the ones. This is 8 to the 0. That's ones. That's the ones place. That's always the ones place. Thank the gods, right? We got to have a ones place. Because how do I start counting? 1, 2. Okay, we got to have a ones place. The next place for base 10 was the tens. What's the next place for base 8? 8. How do I get from here to here? I kept multiplying by the base. Times 10, times 10. Divide that way. So 8, 1 times 8 is 8. So what's this place? 8 squared, 64. Okay, let me stop for a minute. That is really trippy, yes? And I love the reaction again from some of you guys like, oh shit. Please don't drop. You'll be fine. This is weird, because how fundamental is our number system to you? How fundamental is it? When did you start doing base 10 number system? When you're freaking like 2 years old or something, right? I mean, come on, right? So how fundamental is it to you? Crazy fundamental. I'm talking base 8 now. How do we get a base 8? Well, what if we didn't have any pinkies? We would have had a base 8 number system. We wouldn't even think of it that way. It'd just be the way it was. Go with me here. What number, let me take these off. Let's just not talk about the decimals for now. What number is this, of course? 145, yes? What number would this be? It's not 100, is it? It's 164. 4 eighths, which is 32. 5 ones. So what number is this in base 8? It is the number 101. So let me ask you this. So my speedometer, right? Can you guys envision a speedometer? If I buy a brand new car, start driving it, 1 mile, 2 mile, 3, 4, 5, 6, 7, 8, 9. The minute I start to go past 9, the next thing clicks over, yes? And that represents 110 and 0 ones, 10 miles. If we had a base 8 speedometer, this would go up to 7. The minute I drive some more, this would go to 1, 0. What does that mean? 1, 8. So 1, 0 in base 8 is 8. Our base 10 system, when I see a 1, 0, that means 110, 0 ones. Base 8, it would mean 1, 8, 0 ones. We want it to be immediate, right? And plus, you guys probably are sitting there saying, why the shit do I have to know this? Beyond just the fact that I want you to feel the way your students feel when they first learn this stuff. Do you guys understand? Does anyone know a purpose for like base 16? Anybody ever seen? Probably fewer and fewer of you ever seen it, but HTML code of a web page. What about base 2? Base 2 we all know. Zeros and ones, right? Base 2 is zeros and ones. What's that? Starts with a B. Binary, yes. And of course it's binary because there's only 2 options, right? Oh, sort of, a little bit. Yeah, thank you though. So if you ever, maybe I'll show you this. Whenever you look at a website and the background has a specific color, they use base 16 to identify what color it is. Because I want to have, there's a lot of colors. So if I give myself more options, I have more code for more colors. So there are uses of these bases besides just playing with numbers. There are reasons that we use them in today's society, in today's world. Let me do one example with you, one physical example, and then we'll head out a little early. Go with me, go with me. You can see some of you guys are like, good Lord, stop. Let's say I had a whole bunch, let's say I have eggs. I have a lot of chickens and I'm getting eggs and I'm gonna pack them up and I'm gonna sell these eggs, right? I decided that teaching just wasn't doing it, so I got basically an egg farm. I'm gonna put all these things in there. Let's say that I have a whole bunch of freaking eggs and one carton can hold 8 eggs, right? One crate can hold 8 cartons. Are you guys with me? So one carton is 8 eggs. One crate is 8 cartons. And then one truck the little person there can hold 8 crates. All right, go with me for a second. This is kind of cool, right? If I have 12 eggs, it's going to be a very simple question, but I really hope this makes the connection for the base. How many cartons can I fill up? Yeah, I can totally fill up how many cartons? 1 carton, right? And how many do I have left over? Is everybody cool with what I just wrote down? Does it make sense? Now look at it as if it's the number 1, 4. For us, that would be 14, correct? Does that represent 14 eggs? What does it represent? 1 carton of 8 plus 4 left over, 12 eggs, right? You understand? 1 carton is 8 eggs, yes? Plus 4 loose eggs, 12 eggs. This is base 8. 14 base 8 is the same as 12 base 10. But do you all understand? This is just keeping track of how many freaking cartons and how many freaking loose eggs I've got, right? So what if I had, what do you got, Jeff? 51 eggs. How many cartons could I fill up? 6, right? Now what are you doing? How do you actually do this? What's 51 divided by 8? 6. So you can fill up 6 cartons. And then how many would be left over? 3, right? Is that cool? 6 times 8 is 48, so there's 3 left over. I'll call them loose. So the number 63 in base 8 is the same as the number 51 in base 10. Each place for base 10 just keeps track of a certain multiple of 10. Base 8 is just keeping track of a certain number of multiples of base 8, of number 8, right? So I have 6 8s and 3 1s. All right, so what about if I had, what if I had let's say, let's do, what if I had 83 eggs? Sorry? I'm sorry. Yeah, go for it. Yeah.
I was just letting you know.
Oh, sure. If that ever happens, you don't have to tell me what happened. You can just let out. Now, could I fill up a truck? How many eggs does it take to fill up a truck? I'm sorry, I'm not at the truck yet. I'm in a crate. Could I fill up a crate? How many eggs does it take to fill up a crate? 64, right? So don't I have 1 full crate? Is everybody with me? How many eggs do I have left over? You can do it. Yeah. 83 minus 64, 19?
Yes.
How many cartons could I fill up with the leftovers? 2. So this is 64, this is 8, right? So if I fill up 1 crate, that's 64 eggs. So I have 19 left to do something with. Then I can fill up 2 cartons, that's 16. How many eggs do I have left that are loose? 3. So 1, 2, 3 base 8 is the same thing as the number 83 base 10. Okay. So the math behind this is not going to be that hard. What operations did you guys just use? We use division and subtraction, exactly. We're going to divide and subtract to figure out what's going to go there. Okay. So we're going to do, we could do any base. We could do base 2, base 7, base 8, base 9, base 3. Okay. So that's kind of like what's in our future. Okay. All right. I think that's plenty for today. So you guys, for homework, you could definitely start section 2.1. If you aren't able to get the textbook, I'm doing everything I can to try to get at least some copies for you. Probably just gonna go ahead and buy another book for myself so I can make copies.
But you said you had the electronic version, right?
Yeah, but when I go to print it, it includes the answers for some reason.
Hypothetically, couldn't you just like copy the page without the answers and put it in a
Yeah,
Google document?
so I could, I was trying to put it so I could put it up on Canvas, so I was trying to print it as a PDF. So I could just print some copies out. How many of you guys, by the way, don't currently have access to a book? Okay, so I could just do that. Yeah, I could bring copies next time. Yeah.
I still need access to this.
But you're enrolled in the course,
Are
right?
you?
Yeah, well, you
Are you
gave me
teaching a session?
permission.
You have your position in, because I go down
Yeah, so if I gave you authorization to add, you still have to go add.
Yeah, I did have it.
Okay.
She never gave me information about that.
Pretty sure.
Okay. Yeah, the system is not
He's the most intuitive one to work with.
Hey, I'm in a construction course in Missouri. Do you have any elementary teachers that I can work with? That's what I would do. I know somebody. I live in school, so. Oh, perfect. Yeah. I just.
So if you want to,
I
if you have a minute, we can go back to the office. I can make sure you're actually on the on my roster.
Yeah, I don't have any classes after this, so.
Because the day after you enroll, you should have access to campus. It's supposed to be like an automatic rollover.